A very good evening to one and all. Thank you for coming for lecture one of the data driven astronomy course. So I think most of us are here and I'll start the lecture today. So this is the first lecture in this course, and I hope like the last week was interesting for most of you all. I believe most of you are confused and don't have much idea what we are doing, but if you are there then it's exactly where you're supposed to be. So the first week, the aim was not to directly enter into data-driven astronomy, but to try and show a new way to learning itself. So most of us got interested in astronomy because we were curious about the universe, how things work, and we always explored how things work. But somewhere along the line of the education system, we forgot to be curious, and we got used to this method of giving a problem, giving the solution, and doing it, practicing it 100 times, and just vomiting at the exam. But we sort of left behind this curiosity, which led us to fall in love with astronomy itself. So our objective was sort of to try to revive this curiosity so that when you have a random new problem which you have never tested or never seen, but you have the basic skill, we just wanted you to explore on your own before we give you the solution. Because uh, if you are new to programming, you must know this one thing is learning to code and to do coding is a very different thing. If you know the basics of a programming language, everything comes down to the programming logic, which comes out of practice. So if you are learning a new library, for example, say AstroPy or Fort Utilis, if you understand the programming logic and you have some idea of how to play with the code, and it's actually very easy to learn any new package. So initially, when the in the first week when most of you just opened the notebooks, I think a lot of you got scared because it looked completely random and new. But I'm actually happy to tell you that a lot of you have solved. This is actually the number is comparatively much higher than what we had in the first week in the last two sessions. Maybe this it's because this time we screened and tried to make sure only the people who are actually interested participate in the course. But I think the point is put across to most of you because we see that many of you played with the code, came up with different multiple solutions, and explored and noted down your own observations. But if I think even though many of you solved it, some of you still haven't got what we were going for, but you don't have to worry. If you have coding difficulties, we'll help. We are more than ready to help you with, and many people have benefited from the four of us in the course of last 1 week. So coding wise, the 1 week length is given so that you have enough time to explore, and it's there's you don't have to worry if you're not getting the solution, and you have to make mistakes, and that's the most important learning from this exact alternate approach to learning. And it is based on this one uh, tidbit that I found out from Richard Feynman's book on surely must be kidding, Mr. Feynman. And there he talks about when he was in college and in school, he used to do this one thing where he hears a word or comes across a topic that he hasn't heard before. He tries to do this one thing where he tries to guess what the topic is or guess what the concept is. Then once he has set up his mind, then he goes and reads about it, then finds what it is actually. So what it does psychologically is you have what it is and you have list of all the things that it is not. So it sort of embeds in your brain much better. So through this lecture, the goal is actually to connect whatever is in the module. We surely will be discussing the coding part. So if you didn't get the puzzle solutions or you're stuck somewhere, we'll go through that also at the end of the lecture. But through this introduction to multiwavelength astronomy lecture, my aim is to show you why did you do what you did and what is the impact on the scientific impact on this study, like what all can be done using the methods that you explored and what has been done using these methods. So let me start. So if you are with me, can you drop a yes in the chat? like if you are okay with me proceeding ahead. Okay, great. So I want to tell you that if at any point if I'm rushing through or going very fast, or you want to get a bit more clarity on any topic, you can stop me anytime in between. I'm actually trying to record the sessions for the ones who have network issues and the ones who couldn't make it to the class. But in case we're not able to record or the recording is not proper, so I suggest that you can stop me anytime you have a doubt. So I'll begin. So, as you all must know by now, the primary source of information or data that we have in astronomy is through light. And from our very basics in college education and school, we know that light is part of the electromagnetic spectrum, and that light is an electromagnetic wave. And we know that it's other than what we perceive, which we classify as the visible light, there is an classes entire class of uh, different bands of spectrum that we studied at different portions in our academic career. So we must have heard about gamma rays, X-rays, ultraviolet, infrared, microwave. So all of this is part of the electromagnetic spectrum. So, but we humans are limited to the visible band. So it's not special. Why visible? It's only that we are only able to see this portion of the electromagnetic spectrum. And there's actually a very interesting reason why that is. So I'm not sure how many of you must be knowing. So if you look at the solar spectra, the sun's surface temperature is about 5000 Kelvin. And if you check the corresponding black body temperature, that which is using the black body temperature, if you find the corresponding peak wavelength, it falls in the middle of the what we call as the visible spectrum. So the reason sort of why everything on Earth is around visible spectrum is because actually of the sun spectra. It's because sun peaks at optical spectra. So in order for plants to have maximum power transfer, it naturally adapted to the wavelength where the sun is emitting the more. So if you apply that logic, if you were in a solar system where the star peaked in say ultraviolet, the creatures there would have had sort of pupillary devices, if may, would have been able to see the entire universe in ultraviolet. So it's interesting that how much of our surrounding is dependent on how how what is the surface temperature of the sun and what wavelength it emits. And it's interesting that now we are living in a period where we understand what sort of why the reason some of our uh, the things that we see on earth, why they are the way they are. So moving ahead, so as I said, we are only able to see the universe in the surrounding in optical. That doesn't mean there is nothing interesting happening in the other wavelengths. So when we look at the universe, we look out from earth, look into other galaxies, and we look at different electromagnetic bands, we see that we see the universe in different colors. And by colors, I mean we see different phenomenons and different physical mechanisms occurring at different wavelengths. So this sort of tells you the importance of why we should study or look at the universe in, if possible, all wavelengths. Because if you have done basic atomic and molecular physics, you must know that different wavelengths and different radiation pattern actually correspond to very different physical processes, and that could tell us a lot about the galaxy stellar population, metallicity, its star formation history, everything. So in this picture you see the Whirlpool galaxy, which was actually part of the very first section in the module. So in the module, you actually made the optical image using the DSS2 survey, to which we'll be coming later. But now focusing on the multi-wavelength astronomy aspect of it, we see that at different wavelengths, we are able to see very different structures. So in the optical, we see these spiral arms, we see some bluish tint. But when we look at the X-ray image, we see a totally different shape. So whenever in the throughout the lecture, when I use the word morphology, it effectively means shape. You don't have to think deep there. So we see that in all the images, the morphology of the galaxy is very different. And it's interesting to understand that each image corresponds to a very different physical phenomenon. And in this lecture, we'll try to like just briefly understand some of the mechanisms that are involved in each band. Now, the question is, why are we not exactly able to look at the entire electromagnetic spectrum from the Earth? So it's because of the Earth's atmosphere. We have very small windows, pockets in the electromagnetic spectrum where we can look out through the atmosphere, and we'll be able to observe something. It's so you must be familiar that we don't get a lot of UV rays, and that's why we don't get cancer that easily, because sun's ultraviolet radiation gets absorbed by atmosphere. So even though it's a advantage in some cases, but in astronomical cases, it's not that good. So in the figure, you see that in the top you have atmospheric opacity versus wavelength plot, and opacity is generally if it's sort of like transmittance, the opposite of transmittance. If something is not very transparent, then it's called as opaque. So opacity is a measure of opaqueness. So we see that at the very lower wavelengths, our atmosphere is very thick, in sense it's very opaque. And then we have the small optical window. Then we have some regions of the infrared wavelengths which we can observe. Then right after that, the only window we have is the radio window. And for observing in different bands, we require different technology. And since some of the wavelengths are not observable from Earth, we need to have space observatories. So we'll actually go from left to right, that means shortest wavelengths to the longest wavelength, and looking at some of example surveys that will be available. And this will basically make clear of all the acronyms and different names that were put in the module. And so the telescopes and surveys that I'm showing you are not the most updated one. And the reason for that is, for most of our projects and exercises, we'll be using something called as the archival data. So whenever scientists observe or give a proposal, they have proprietary right over the data for a set amount of period. It could be 3 months, 6 months, or 1 year. After that, it is released to the public so that everybody can use that data. So such data gets collected and accumulated in repositories, and that can be used for something called as archival data science. So it's interesting to know that in the last decade, more than 60% of the science actually came out of archival data science rather than proprietary data. So to understand and know what all archival data is available and how to access it is very important. So the first week module, as it is named Acquisition and Visualization, teaches you how to acquire data using a particular mode. It's the server is called as NASA Skyview, and you are using some sort of API to make these connections to all these the NASA Skyview server. So let's go to the first telescope. So the first telescope is the gamma ray telescope. So it's sort of an artistic rendition of the Fermi Gamma Ray Telescope, and on the bottom right corner you see the all sky. It's basically the 3D 2D projection of the entire sky, and this sort of gives us what the uh, gamma sky looks like in the gamma ray
Hello,
band.
Avinash.
Yeah.
Your voice was breaking when you were talking about archival data.
Okay.
So
So
repeat that part.
okay, sure. So uh, yeah. So whenever a scientist makes a proposal, like they'll have something called as the proprietary period. It's the duration of the period where the data is only available to the scientist who proposed the project, and after that period, that data is made available to the public to explore. So this is because you might be observing a particular source for your science objective, but that same observation can be used by somebody else for a different science objective. So what happens is, since astronomy has progressed from normal eye view to looking at the telescope and drawing to CCD cameras to digitized data to large databases of data, these proprietary data have been made available through different archives. So the one archival data that you all have explored, knowing or unknowingly, in the first module is the NASA Skyview repository. And the Astro query is sort of like a wrapper which accesses this Skyview server. And there are actually multiple ways to uh, eh, like access these archival data, but doing it in a scripted programming module sort of lets you automate a lot of processes. So the one other aspect I was talking about archival data is in the past decade, more than 60% of the science that was reported and published came out of archival data than like proprietary data. So it's important to know how to acquire and how to use archival data. So that's what we looked at in the first module, which is why it is named acquisition and visualization. So is that clear? Shall I move ahead?
Yeah.
Yeah. So the first telescope is the Fermi Gamma Ray Telescope. The image that you see is an artistic rendition. And on the bottom right corner, we see a 2D projection of the 3D sky that the Fermi Gamma Ray Telescope observed. So I'll tell you one more features about these observations, that sometimes telescope go as something called a survey mode. In survey mode, the telescope, irrespective of proposal, will have during the telescope proposal project planning itself, they'll decide that it is going to observe the entire sky and it will produce a map so that we have observation of every part of the sky. So this allows us to, this will be a lower resolution, less sensitive survey, but this allows us to see how the sky will look in a particular wavelength using a particular telescope. So this bottom right image that you see is such an image. So this is the 2D projection, and we see this is how the uh, gamma ray sky looks like. So what you see in the middle is because of the Milky Way galaxy, our Milky Way. So we can't, and when we look along the Milky Way, we only see we are not able to see the center nor outside because the Milky Way will sort of obscure whatever is behind. So this entire sky image allows us to understand how the gamma ray sky will look like. And on a side note, this particular telescope, Fermi telescope, looks uh, at energies 10 kilo electron volt to 300 giga electron volts. Moving on, so this is the Chandra X-ray Observatory, and this is sort of a very popular mission, and it has quite a lot of history. So Chandra X-ray Observatory, as its name suggests, observes in the X-ray domain and observes in the wavelength zero point 0.1 to 10 kilo electron volts. So as you must be knowing, gamma ray and X-rays have very high energy density as electromagnetic radiation and often are uh, seen as signs of high energy processes such as like X-ray jets or hot gas or star forming regions. So if you know from your basic optics lessons, there is a resolving power equation which is as the resolving power of a particular telescope is 1.22 times the lambda, which is the wavelength the telescope is observing, divided by the size of the aperture. So this essentially tells you that the resolving power, which is basically the smallest angular separation the telescope can differentiate, is directly proportional to the wavelength. So smaller the wavelength, higher will be the angular resolution. That means you will be able to resolve two small angles much better if you observe it higher frequency. So X-ray and gamma ray sort of that's why gives really high resolution images, even if the telescope aperture, which is the diameter of the the primary mirrors, even if it's not big, you can get really good resolution. So, so Chandra X-ray Observatory as such didn't do an all-sky survey. So, but E Rosita, which is another X-ray observatory, it did do a all sky survey, and in the bottom right, I've shown the all sky, sorry, the the 2D projection of the X-ray sky uh, on the bottom right. So moving to the next. So next we have infrared. So this I've sort of missed out the, what do you say, the order here for another reason, that these are all uh, old telescopes. So I sort of put them together. So the WISE telescope, which stands for Wide Field Infrared Survey Explorer, looks at the infrared part of the sky. And it actually has multiple bands like 22 micron, 12 micron, 4.3 micron, 3.6 micron. And all these wavelengths have very high significance in the astronomical perspective. So whenever an observation is, a telescope is planned and designed, a lot of theoretical feedback goes into its design. So at some point, like I'll discuss about the how, like, what sort of work is being done from the Indian side towards such multi-wavelength observatories and space telescopes. But as of now, WISE is a telescope which gave us a lot of insights on, like, IR re-emissions, and it also discovered quite a bit of exoplanets and brown dwarfs. So WISE is a very important survey, and it also has an all-sky publicly available data through NASA Skyview. So next we have the SDSS survey. So this is one data that you actually used in your modules. So SDSS stands for the Sloan Digital Sky Survey. It uses the 2.5-meter Sloan Foundation telescope at Apache Point Observatory. So this particular telescope is very important in our course because we'll be using many different surveys and results that this particular telescope got. So a lot of scaling relations that we use in astronomy was actually in the last decade was made possible by the SDSS telescope. For example, whenever we have scaling relations for, say, the star formation rate or the specific star formation rate, it's okay even if you don't understand these jargons, but essentially what I'm trying to say is a lot of data in spectroscopic and imaging wise was made possible through the SDSS telescope, and we'll be using quite a bit of it in our entire course. So next is the Galaxy Evolution Explorer, which stands for GALEX, which is actually GALEX, and it looks at the UV part of the sky, and it mainly has two bands, which is the NUV band and the FUV band. So Galax actually has not that great a resolution, but it did have an all sky survey, which allowed us to look at a lot of UV counterparts of the optical galaxies and the optical phenomena that you see. So I see that it's 5:30. So and we have actually covered one major section of our course, the lecture today. So, if you guys want, we can take a break for 5 minutes. If you want a break, just drop a yes in the chat. Or if you don't want a 5 minutes break, you can drop a no. Yeah, good. So, the Galaxy Evolution Explorer is the particular the telescope. It also is available in NASA Skyview, and you can use it to look at the UV counterparts, which actually tells you about energetic processes such as star formation, AGN accretion, or mergers. So these are the some telescopes and some surveys that we'll be actually using in our uh, multi-wavelength observations. But apart from this, as I showed in the initial, there's also the radio wave observations. In this particular presentation, I haven't included much of radio observations because the physical mechanisms that are actually explored using radio surveys is quite physically, like the physical mechanism that undergoes is a bit difficult to grasp, and I didn't want to confuse you at this stage. But if at a later point, if a lot of you are interested, we can even explore radio astronomy and radio astrophysics. So now that we understand some of the telescopes that are available and where they are, we can look at what sort of information can actually be gathered from the image analysis or image procurement you did. So I believe all of you must be knowing black body radiation. And we know this one key feature of black body radiation is that it is temperature, it depends on the temperature. So for each temperature, there is a unique black body curve. So if you remember from the black body radiation derivations, there is one approximation which is called as Wein's approximation, and it gives you a law called the Wein's displacement law, which gives you the uh, proportionality relation between the peak wavelength and the corresponding blackbody temperature. That means if you know the for a blackbody, if you know what wavelength it is peaking at, that means you can give its corresponding temperature. So this is actually a very useful result when you're doing multi-wavelength observations, and I'll try to show you how. So imagine you are looking at the optical image. You're looking at the optical image and you know what is the wavelength of the particular observation, like which wavelength that particular optical observation is shown. And from Wein's displacement law, you can find what the corresponding temperature is to that particular wavelength. Now, assuming that what you're seeing is undergoing the blackbody mechanism, we can find out what the temperature is. So, for example, say you're looking at the a blue, you see that there's a lot of blue part in the image, and this particular image is RGB image. But we'll come back to what RGB image is a bit later. But using Wein's law, what you can do is, if you know the peak wavelength, you can find out the temperature. So for now, I want you to just remember this and keep in your mind that if you know the peak wavelength, you can find the temperature, given the key assumption that it's the radiation mechanism is black body radiation mechanism. But we know that black body radiation mechanism is not the only way to get radiation. There are a lot of physical processes which can have uh, give rise to radiation. So we have radiative transfers. I'm not going to go individually into each of these processes because each will require one course. But in generally, we know that there are many processes. So that we can get emission lines from like this quantum radiative jumps, like absorption, emission. All these processes could happen. We can also have processes like Bremsstrahlung or synchrotron radiation based on the physical situation of the where the emission is coming from. And what we essentially get because of multi-wavelength astronomy is, see, now from a single wavelength you can only find out if the mechanism which is causing the emission, if it is black body. If it is not true in other cases, for example, if it is synchrotron or Bremsstrahlung sort of an uh, emission process or radiation process, you need observation at multiple wavelengths to make something like what is shown in the slide. So this is called as spectral energy density diagram. So here we have flux versus the frequency. So what tells you the radiation mechanism is where it falls, what sort of slope the radiation has. So the slope tells you what sort of physical process is causing the radiation that you observe. And one interesting feature that you see is there are points where the radiation could be because of multiple processes. So you can't simply actually say just based on the wavelength that this is the temperature. So if you know that synchrotron and Bremsstrahlung radiation are non-thermal radiation. That means they have no temperature correlations directly. So this is the synchrotron radiation is what fuels most of radio astronomy, and it's a bit theoretically involved. So maybe at a later lecture we'll go a bit more depth on synchrotron radiation and how do we observe it and what sort of projects can be pursued using the data that we have. So Now, as I said, like a lot of observations that we and a lot of exercises that we did using either IR or optical, or in some cases UV data. And to most extent, most of them do come in thermal radiation. So you can use Wayne's displacement law to say what the corresponding temperature is. But now when it comes to X-ray, gamma rays, and even including radio, you can't exactly do that. So that's why if we include that also, our problems becomes way more complex, because then we'll have to do these SCD fitting and spectral index analysis. So that's above the what's aimed for this course. But so for the our analysis till the course project, let's limit our study to infrared, optical, and ultraviolet uh, radiation and those sort of data. So in the exercises, you must have seen this word being used again and again, which is filters. So STSS has these many filters. So essentially, it is very similar to the filters that we come across in our electronics class, where we have low pass filter, high pass filter, band pass filter, band block filter. So we know that, and I think most of us understand this. Essentially, what it does is it removes or keeps a particular section of the radiation that we're getting. So in electronics, we do this with frequencies. If we want to limit, we only want from this frequency to this frequency, we keep a band pass filter. So we get radiation, or we only get oscillations in that particular frequency. So very similar to that, there are filters in astronomy where we try to get specific sections of the electromagnetic spectrum, as each give us very different information, as we understood from the multi-wavelength astronomy brief diagram. So each wavelength, each filter will tell you a bit different information. So from very basic black body radiation study, we understand that red has a higher wavelength and blue has a lower wavelength. So applying that logic to Wayne's displacement, if something is blue, that means it has high frequency, that is low wavelength, that means it has high temperature. So I'll sort of say that again. We know that red has higher wavelength, green second, then blue has the smallest wavelength amongst visible RGB colors. So right now I'm talking about visible red, visible blue, and visible green. This will be important at the later stage. So now if we apply the Wayne's displacement law, blue, since it has the shortest wavelength, it will have the highest temperature. So amongst RGB, blue will have the highest temperature. Similarly, this exact logic amongst RGB, T amongst RGB, red will have the uh, relatively lowest temperature. So whenever you look at an image and you know it is giving you visible RGB colors, and you see something as blue, you know that it has higher temperature. Now we'll try to uh, make this understanding and make this concept like root in our mind a bit more deeply through couple of examples. So yeah, let's start by understanding what do you exactly see when you make an image. So the very first thing that you did in the exercise was to use the FITS data and make plot the image. So if you look at the image, you'll essentially see, if you had seen the array, it is basically a 2D matrix of different numbers. And what you plot is basically the relative intensity or the relative amplitude of each uh, positions in the 2D matrix. So such plots are called as intensity plots. And this is not only used in astronomy, to anywhere where we have a parametric field which has three parameters. We often use the put two parameters in the coordinate axis, and we put the third parameter in the color axis. So when you're looking at a galaxy image, you're essentially looking at position versus brightness. So you are getting for each position what is the brightness that you're getting. So this is called as intensity plots. Now from the very first slide that I showed you, we know that we can only see the visible part of the sky. So how do you see X-ray, UV images if our human eyes can't capture those wavelengths because we are limited that way? So here is where this one astronomical technique comes called as false color imaging. And I believe a lot of you must have faced this issue that why are we putting red in blue when we have a red filter. So what is the convention is, since we can't see UV or IR radio, we assign a color that we can see. So say you're looking at X-ray observation of a galaxy. Now you can't see X-rays. So when you do the observations, what you have is numbers. So all of you have used different color maps while you were making the images using matplotlib. So very similar to that, you assign a color to each number, because what you essentially have is a 2D distribution like this with the third axis of amplitude. So what you do is you assign a color for each amplitude. You'll say that if it is 0, it will be black. If it is 1, it will be white. So you're sort of giving a color map. So most of the pretty astronomy pictures that you see, if you went in real life and looked at those, it won't look that pretty at all. So those things are called actually true color images, which is all the colors that they use are transcribed into the colors which how human eyes would actually perceive. So most of the astronomical images that we see are such false color images. So let's see a small example again using the Whirlpool galaxy. And this is the very first RGB image you all must have made. So the processes that are given to make these images are simply routines. So they don't have any explanation and they don't require, because that is just a method to see. So when you go for different method, there'll be different routines. So it is essentially like learning a tool. So if you have a pencil, you write, you don't have to learn to write every time you get a new pencil, right? So it's essentially a different pencil, but the logic still applies. So every time you open a package, the documentation will tell you how to use it. So you won't always have to learn or watch a video how to use the package, because plenty of documentation is available. But to know what to use it for is where the you need some sort of input, and that's what we are going to do. So I have three images which I have procured from NASA Skyview. The first data is from DSS to IR. So DSS is another survey. It stands for Digitized Sky Survey. So it is the digitized version of the Palomar Sky Survey. So this happened in the early, I think, couple 50 years ago, when we used to use uh, this these photographic plates to do astronomy. And we used to there was a time when photographic plates started degrading. So the digitized mission, what they did, they digitally scanned each of these photographic plates and digitized them. So hence the digitized sky survey. So if you actually look at in these some of the images, sometimes you will see some artifacts of photographic plates. So now coming back to the topic at hand. So these are three different images of the same galaxy observed in different wavelengths. So DSS to IR is observed in the infrared wavelengths. DSS to red corresponds to observations in the optical red, and DSS to blue corresponds to the optical blue. So I hope this is clear. So we have IR, optical red, optical blue. Now since there is no meaning to color here, since IR we can't essentially see, only red and blue see, what we are gonna do is gonna do false color imaging. We'll assign a color to each of these data. So I'll assign red color to DSS to IR. So red color means it has the highest amplitude, and if it is black, that it means it has the lowest amplitude. Similarly, I'll assign green color to the DSS to red. So it is just a convention that you usually go in what you say, increasing order of frequency. So the lowest frequency will be red and the highest frequency will be blue. So that is the reason you'd see that DSS to red doesn't always mean that I have to put it in red color. So since I have put assign the color, to be honest, we can put any color, any image in any color, but there is actually a logical reason why we prefer this convention of increasing order of frequency. So now, since I have one color assigned to each, what I'll do is I'll combine the image and we'll get the RGB image that we get. So now a lot of science can be done by simply looking at this image. And from experience, what I found is artists make most observation from this image than physicists, because we go after there is a black hole, there is this tidal winds, and there is merger. But artists can find out most. An art person will first of all say it looks blue and there's sort of a red hue. There are these two white smudges somewhere, and there is a pretty spiral structure. And that simple observation has a lot of physical consequence. For example, like when I started talking about Wayne's displacement, we see that this particular image has a lot of blueness in it. So a lot of that implies whatever we substituted in the blue filter has a lot of influence in this image. So relatively, whatever is in the blue filter has maximum influence on this image. Now, in our case, the blue filter corresponds to optical blue, but that might not be true always. I could put UV in blue, I could put radio in blue, but that only means that whatever survey I have assigned to blue color is peaking. So now let's do a bit more astronomy by just looking at this image. So since all of this, majority of the uh, what we see in the image is blue, we can say that using Wayne's displacement law, that whatever C has, we are seeing has high temperature. If you actually go and substitute the wavelength, it will come of the order of 10,000 Kelvin to 15,000 Kelvin. So that corresponds to very hot stars. So stars which are young. And now the opposite is what is true for red. So we see that some part of the spiral arm has red obscurations. So whatever corresponds to these red obscurations could either be absorptions or could correspond to stars which have lower temperature. Now, at this point, we can actually make a lot of physical predictions using simple physics. Now, we know that the energy that any object which follows all thermodynamic laws is limited. You only get a fixed amount of energy to do anything. So even if it's nuclear reaction, after a certain time, it does run out. So if we have a fixed energy, and since these stars have higher temperature, that means they are expending higher amount of energy. If you're spending more energy, spending energy more faster, that means you'll spend it in a very short time. I'll say that again. So blue stars, since they have higher temperature, they must be having higher energy output. If they have higher energy output, that means they must be dying fast. So all the stars that you see in blue by this logic are young. And backtracking the same logic we can use for red. If something is spending the energy slowly, and that means it has low, if something has low temperature, it must be spending the energy at a longer time. That means those stars could be older. Now with young stars, if you say that something only lives for say 2 years, and you are seeing that thing there. So if you are able to see something which lives 2 years, that means it must have born in the last 2 years. That means it's young. So basically concluding whatever I said in the last 5 minutes, if a star is blue, that means it has high temperature, it is massive, and it is young. So if it is young, so also that if it's high mass, that means it's short-lived. The very exact opposite works for whatever you see in red if you're looking at optical red. If it is red, the star is low mass, older, and it has a lower temperature. So by just looking at the image and knowing which color corresponds to which electromagnetic band, we were able to find the age of the star, the size of the star, and which stellar population it corresponds to. And we see that theoretically that is very true. We do expect to see a lot of young star formation and massive stars in the star forming regions along the spiral arms. So this sort of analysis gives you a very not a very critical analysis, but gives you an overall analysis of the stellar population and the age of the galaxy and the mean stellar age of the galaxy. Now, from the shape of it, we see that there is a spiral arm-like structure, and from knowing basically how whirlpools work, we can see that this galaxy might be rotating in anti-clockwise direction. So it is pretty logical, right? You just have to see where the retrieving end of the spiral arm is pointing towards. So it's sort of rotating in anti-clockwise. And we also see that there are two regions which are white in color. Now this is important. If we look at the colors that which we made to use it, which is RGB, we know that we get white color when we mix red, green, and blue together. So if they all have come in equal intensity, they make white. So we know that the information is whatever is in the middle is emitting almost equally in all three bands that are used. And from sort of basic extragalactic astrophysics, we know that almost all, in a sense, all the galaxies host a supermassive black hole in the middle, and they are known to have such broad emissions. So that is the reason we are seeing white. So if this is a black hole, that means whatever emitting here must also be a black hole, which is exactly true. So this is Whirlpool galaxy is a merging system where the bigger spiral galaxy is eating up a small, like sort of a dwarf galaxy. So all of this information is simply by knowing what band, what color corresponds to what survey. So now this is true for any galaxy and any survey. So the analysis that you can do with this, whatever we did in the very first module, is called as RGB analysis, and it is something very popularly done and very useful technique to do in extragalactic astrophysics. So by looking at the shape, you can tell what sort of morphology the galaxy has. And there is actually a lot of star formation dependence on based on where you see the galaxies to be. So originally, the what you see here on the top left side is the Hubble Ocular tuning fork. It is actually the extension of Hubble's tuning fork. Originally, it was thought that this has an evolutionary phase, but later it was found that it's not, doesn't correspond to any evolutionary trait, but it is a way to classify the shape of the galaxy. So it starts from very like circular elliptic galaxies, goes to lenticular galaxies, all the way to spiral galaxies. So there's a dependence on star formation and morphology also, which you could explore. You could explore if there is a presence of bar where the star formation is, and how do you look at star formation using knowing which color corresponds to star formation. So now you know that blue corresponds to young stars. So wherever you see young stars must be a star forming region, and all this is assuming that the radiation is from the radiation mechanism that is causing the radiation is black body, which is a good approximation at this level. Now, knowing where the galaxy or the stellar population that you're seeing falls in the HR diagram, it's okay if you don't know what is HR diagram. So this, what you see on the right side is the Hartzell-Russell diagram, or shortly called HR diagram. It essentially gives you a relation between the galaxy's color and luminosity. So a color of a galaxy is the difference in magnitude between two filters. For example, we used DSS2 red and DSS2 blue, right? If we subtract these two, the magnitudes measured in these two filters, we'll get a quantity defined as color. So it is not has much to do with the color that we talk about, but it is essentially telling you whether it is bluer or redder, and that has a lot of significance. So if you understand HR diagram, if you do a very basic look at the Hubble sequence, you can get the shape of the galaxy, which will tell you sort of which phase the galaxy is and what sort of star formation to expect. And from the HR diagram, you can find out what evolutionary stage the stellar population that you're observing is in. So all this is simply by knowing what your image was used to make, and which is exactly what you did in the first week. Although the puzzle is just to keep you interested in the workshop and to make our job of analyzing easy, but the exercises are meant to just teach you how to acquire the data. It's sort of like teaching you, giving you a tool and telling you what to do, how to use the tool, but it's up to you how you use the tool. So you don't always need like a step by step explanation of what the code is doing, because I believe like at the modern astronomy you will be forced to use a lot of packages, and most of the time you won't understand what is happening in the underlying code. For example, one what do you say, one function that you must have used in your module one is make looked on RGB. So there actually goes up quite a bit of data reduction, clipping processes which goes behind the image. But you saw that we were able to reproduce a percentage of that using our normal RGB image making method. So you don't always need to understand how the code is working, but it is very important to learn how to use the code. So if you should be able to use a package, even if if nobody is coming to you to teach you this function does this, this function does this, because that is not the logic of learning programming. That we are only learning the program, which is actually a very easy task to do, because you can simply tell this function corresponds to this, this gives this result. But the amount of knowledge you get by using that package in your own sense, making mistakes, you can't have that from simply like learning the program. So to conclude, the first module that you did essentially grasps and grasp the elements that are required for RGB analysis. So what you can do is, now that if you have completed the module, which I'm happy most of you are, you can actually apply what you learned into any number of galaxy you want. So in the module you only looked at couple of galaxies and sources, but you can make RGB images of say some 5 6 galaxies, look at its color, look at its shape, and try to understand what it means. Like is it merging, is it interacting, do you see star formation where it is not expected? Now to know where the star formation is expected, that you will have to do a lot of literature survey, because a lot of has happened in the last like century in the field of extragalactic astrophysics. But what through this course and this first particular module you have is a tool to make those images. Now, irrespective of which project you are doing or which extragalactic science you are requiring, you can make these RGB images. For example, say you're studying star formation due to merging systems. You can use same RGB routine. You can use the UV filter in the blue band and study star formation. Similarly, say you are looking for older stellar population. You can look at which all galaxies look very red. So it also could be because of dust and other properties, but essentially now you have a method and a technique that will make you that will help you analyze an image uh, in a more quantitative way. So now whenever you look at an astronomy image, rather than admiring what the physical features of it, maybe you can look in the description which wavelength this corresponds to, and what temperature is it, and what information can you gather from it. So with that, I have met the goal of what I wanted to tell you with this multi-wavelength astronomy lecture. So if you have any questions with anything that I've covered so far, you can ask me right now. Or did everything just go over your head? So did you all understand at least like some say 70% of the lecture? If yes, then you can drop a yes. So, do you think if I gave you a galaxy name, I gave you a galaxy source, I gave you its data, you can make RGB image and do the analysis that I showed you right now? If yes, then you can drop an ASC again. Like if I give you a source and give the image, can you do RGB analysis? I have one yes for RGB. Yeah, probably yes, we can do. That's good. Does anybody want to discuss the actual code if you want? Because from my colleagues, what I understand that most of you have actually finished the code, and some of you actually have done more than like did very fast. So I'd like to inform you that there is actually it's if you can't do it, that's okay, but it's not like we won't give you incentives for doing things faster. So the people who can handle the coding part well, we'll try to give them more theoretical aspects to work on towards the end of the course project, because like I said in the very first class, this time the workshop we actually have a science goal in mind. So we are hoping that at least out of you 23, a five of you could be a co-author with us in a paper, because the project that we have in mind has a lot of data reduction, and it'll be helpful to get people who are good at this. So the good part advantages of this is, rather than just learning technique and applying it, you also get to apply it in a project and get it as a published result. So if you are willing to put effort and do things faster and put more effort, you will be appreciated for that also. So you don't have to worry about that aspect. So does anybody have any doubts about the RGB analysis, multi-wavelength astronomy, or even coding doubts? You can even tell if you are completely clueless about everything, you have not understood anything and haven't started yet. Even that is fine, because it's still not late. Because from the second week onwards, we'll actually be targeting very specific topics, very specific packages that will lead to our final project. So if you have any doubts, you can clear before we conclude the second week. And even if you want at any point more information like this on RGB analysis, you want more information on, say, radio astronomy, or you want more information on a particular package, you can always say that also. So, any doubts? If you have no doubt, also you can put a no in the chat. So, I believe you understood everything. Yeah. Okay, in the previous assignment, some of the codes that are actually given wasn't run properly. So, Deepali, can you expand a bit more on that? So maybe like we can help you. If it's a quick thing, maybe we can quick help you right now, or if it's a bit time taking, then one of us will like contact you and you can share the collab notebook. So one thing I would like to tell you is the way, if you feel, you don't have to feel shy to share if you don't understand anything, because the exact point is for you to try and make mistakes and learn. So please do try each module, each puzzle, because if you solve the first week module, you must be knowing it's not rocket science. Whatever we show in the previous code is what we ask again repeatedly. So Deepali, can you tell me? You can unmute and tell, or you can type it in the chat box also, like which exact code. Hello. Okay, I'll present the collab notebook. So if you have doubt in any section, you can tell.
So I have
Yeah,
RGB.
yeah. Ask.
Can you show that slide where you show
Yeah.
DSS sample three?
Sorry, which slide?
So the one where we discussed about the DSS sky survey, we had red, blue,
This
and green.
this one.
Yeah, yes. If we are looking at the IR image, see IR is not visible to our eyes, so we should get totally. I mean, nothing data. No? It should be completely blank. We are
Yes.
still able to see something. So how is that possible?
Yes, so here we are not looking at the galaxy, right? We are using a telescope which has a detector. That detector can actually see IR. Now, the detector is what is observing. What the detector gives as output is a 2D matrix with numbers. Now, that doesn't have any information of colors. It is just a detector, just a 2D matrix with numbers. So, the reason we are able to see IR is because the detector can see IR. So the exact same thing works with all observations. We can't see radio, but we can make detectors which can see radio. Same with X-ray or UV. So does that clear your doubt, Amlan?
Yeah.
Great. So yeah, that's even 60% is good. Any percent greater than zero is good. So you have so the reason it spans 1 month is, see, all of these lectures and coursework, these assignments can be done in the span of say 5 6 days. But the entire objective is to so that you actually benefit from doing these exercises, so that we are available to you 24/7 to help you with the science and the coding part. So any sort of progress is better than no progress. So you don't have to worry about your pace. If you are a bit slow, that's okay. So uh, yeah.
Sir, you said that based on our responses or in this assignments, there would be like we would be assigned some last week project. Can you clarify on that?
Yeah, sure. So what we every year do is we divide you into groups, and each group will be assigned a specific topic, and we divide the group based on such that we don't want everybody in the group to be really good. That means at least it will give a selection bias to the other groups. So what we do is based on your performance, we'll divide you into groups such that all groups have each equal performative capacity, and the topics are also chosen based on like how well you performed in the group. So we don't want you to give you a project which is too difficult for you, because it's like some people would be coming from a very good programming background, so we can't give them a very highly physics oriented project. Similarly, somebody coming from a very like pure science background, we can't burden them with a what do you say a machine learning or a deep learning project, right? So the segregation is to your benefit. It's not like a person who does it first is better, or a person who doesn't code well is bad. It's just that this your feedback is very important for us to segregate you into groups. And this time the project, since it's has a proper scientific goal, we are trying to make sure that the people in each group, the groups do perform in a way that we can quantify your performance. So some groups will act as validation groups, and some will be doing the training, and some will be doing the testing parts. So based on your coding performance and how regular you are, we just segregate you into groups. So that's essentially the gist of it. I hope that was clear. Amlan, was that clear?
Yes, sir.
Yeah. So if you don't want to discuss the module right now, then you can drop a note, because I see it's been over an hour, and statistics says that people can't listen to lectures more than 45 minutes. So I don't think like even if I go ahead, it will be of much use. So do you want me to continue, or shall we break for today? Drop a yes if you want to break for today. So I see two yeses. So the rest of you want to discuss the module. If you don't want to discuss the module, then you can. What should we do? Thing is, let's do one thing. Let's break for today. because I see many people will be submitting tonight, and if there are people who still have problem with week one uh, puzzles, we'll have a meeting like this specifically for them, so that the ones who finish they can move ahead. Is that okay? I believe that should be okay. So, okay, okay. Thank you for attending the session. I'll try to upload the video in Positron channel and share the link. So for the ones who couldn't, who the continuity broke, they can check up any part. That's all. Thank you, everyone.